We keep talking about ideal gases. What about real gases? And what makes a gas ideal? Right? Is it a model citizen? Does it look really nice? The characteristics of an ideal gas are that it has no attractions between gas particles. That's part of what kinetic molecular theory says. The particles don't interact with each other. And a negligible particle volume. The size of the particle itself doesn't matter. Well, under relatively normal conditions, such as STP, real gases behave very much like ideal gases. And so we can look at this table here. We're calculating the actual molar volume of different gases at STP. We know that it should be 22.41 liters. For chlorine, 22.06, 22.31, 22.4, 0.4, 0.41, helium hits it, 22.42. Those are all really close, right? At standard temperature and pressure. But if we get to really high pressure or really low temperature, then they don't act ideally. So let's see why. So at low pressures, the volume of the argon particles is negligibly small, but if we increase the pressure and push them all together, now their size matters. So let's think about people getting into an elevator. Let's think about our class getting into an elevator, right? So here we are, and we go over and we try to crowd into the elevator, and now the sizes of our bodies matter, right? If this was a chemistry class with the O-line of Fresno City football players in it, these are all big guys, they're not going to fit in the elevator, right? Or maybe we have, people's children, a whole bunch of kindergartners in here, and they try to get into the elevator. They're a lot smaller, right? So in that compressed space, the size of the particle matters. Whereas in the classroom, it doesn't really matter, right? So here, because the pressure is so high, the particles are so close, now the actual volume of the particles matters. So here we see that as we increase the pressure, the volume of an ideal gas is here, and the volume of an actual gas is larger. Because as you squish them together, you're going to get to a point where the size really starts to matter. An ideal gas, I guess theoretically, you could squish it to 0 volume, right? But you can't do that with a real gas because they do have volume. So there's a modification of the ideal gas law to take into account what happens at higher pressures. And it was Johannes van der Waals that came up with this. And it's really awesome that they did this, but we're not going to use it at all. So at high temperature, pressures of gases are also very close to ideal gases, because the gas particles have high kinetic energy, and so when they bump into each other, they don't have time to interact. At lower temperatures, lower kinetic energy, now as these particles interact, as they collide, they have time to interact. So if you think maybe about people passing each other on a New York City street sidewalk, right? Do you get into relationships with people that you pass? No, because you barely see them, right? It's just bing, you're gone, right? Maybe, that was kind of cute, but you're gone, right? Let's think about speed dating. So now you're sitting at a table with somebody for a minute, or whatever they do, right? It's not very long, but it's long enough that you can interact with each other. So at lower temperatures, because the particles are moving slowly, when they run into each other, they have time to say, hey, I kind of like you. And so their collisions are not as elastic. And now the interaction between the particles starts to matter. So what we see here is the effect of the intermolecular attractions. So as the temperature increases, the gas behavior becomes more ideal. When it gets slower, the pressure that we observe is less than the ideal gas because the particles stick to each other a little bit, and so they don't take up as much space. Again, there's a conversion thing for the van der Waals a conversion for the ideal gas law, and then you can put both of those corrections on there, and gosh, that makes the ideal gas law seem awfully nice. It's just PV equals nRT, right? That exists. We're not going to do it. This is looking at ideal behavior. So an ideal gas, here we're looking at the significance of intermolecular attractions, really. So ideal gas is here, and we can look at different pressures, and we see that helium is going to go really high. Helium particles are very small. Their intermolecular attractions are very weak, and so it's really not affected. But water molecules do have a lot of interaction for each other, and so we see this big effect for water. I think I just said that all wrong. So here it's the intermolecular attraction. So I kind of got it right. I didn't read the words. Intermolecular attraction is most important for these that are dropping below because they're kind of sticking to each other. The ones that are deviating above, there it's the actual size of the particles that matter. Helium doesn't have much interaction with each other, but eventually it does have a size when you get it compressed enough.